let's keep going with the things that we were learning just a moment ago. So in particular, let me refresh your memory from mere minutes ago about what we were doing. We had this distribution, that the beta distribution over 2 objects. We had a random distribution over k objects, and now we have this random distribution over infinity of objects. And the interesting thing is, I started out with this outline of I'm going to tell you what a Dirichlet process is, I'm going to tell you what a Chinese restaurant process is, etc. And technically speaking, I have not yet done any of those things. So let me now finally define a Dirichlet process. Oh, there's a question.
Sorry, when you do the GEM, you fix a certain parameters, right? So compared to discrete, Dirichlet trials, we lose by fixing those parameters. Do you lose anything?
Oh, is the question how to choose the parameter in the GEM? Okay, so right now we've developed this sort of generative model for how you have a random distribution over these probabilities. And you could say that the alpha parameter is a parameter of that model. And so if we're good Bayesians, we can do the usual Bayesian things with that. We could say, let's put a prior over that parameter. It turns out there are various ways that we can learn that parameter. I'll probably talk more about it later. We could do something empirical Bayesian. We could set it via some sort of empirical procedure like that. But right now, I'm just going to continue talking about the sort of generative model.
Okay, sorry. Also the one, how we fix that? Why?
Oh, why do we choose the 1? It's convenient. Yeah. So there's an interesting thing in general in any sort of modeling, machine learning that you do. There's always this perfect thing that you wish you were doing, and it's absolutely the most lovely thing, and it would be great. And at the end of the day, you have to make some sort of computational statistical trade-off. You have to make a trade-off in what's feasible, what can you do quickly, but will still have good statistical properties and good machine learning properties. And so this is one of those trade-offs that we're making. And I'll talk at the end about why this might be a bad trade-off and some better choices you could make. Okay, great. Let the anticipation build up no longer. What is the Dirichlet process? So this is just Dirichlet process stick breaking maybe, but the actual Dirichlet process is something a bit more. It's when we combine all of these things. So what we're going to do is we're going to have our probabilities from the GEM, and right now we just put those probabilities on the integers. We said row 1 is on 1, row 2 is on 2, row 3 is on 3. So row 1 is the probability of 1, row 2 is the probability of 2, row 3 is the probability of 3. And to form a Dirichlet process, we're going to change the locations of these probabilities. We're going to say that they're probabilities of different things. And in particular, what we're going to do is we're going to say that the locations are IID from some distribution. So that's what this means here. I'm just saying locations phi from some distribution G0. G0 could be any distribution. For the purposes of my example in a moment, you can think of it as like a uniform distribution or a normal or something like that, but it really could be anything. And what I'm going to do is I'm going to plot this G, and I'll explain what that means. So here's what I've done. So for this illustration, we can pretend for the moment that the space is just the real line. And we can pretend for the moment that I drew my phi's maybe normally distributed on the real line. And so what I did was I took row 1 and I put it in an IID normally distributed location. And I took row 2 and I put it in IID normally distributed location phi 2. And that's how I came up with this figure here. And that figure here is represented by this formula here. So G, it's called a random measure. And all this formula is saying is put mass rho k, put probability rho k, at location phi k. So this is a Dirac delta function. It puts mass 1 at phi k, and then we multiply it by mass rho k. So we're just putting, here we have a distribution over the integers, here we have a distribution over something else. That's all this is saying. And then this is going to be a Dirichlet process, and I'll say in a moment why we care. But this is going to be what we define as a Dirichlet process. It'll be a random distribution over some space, some capital phi. So it's not just a random distribution over the integers now, it's a random distribution over some space. Okay, and the way that this is going to be important to us, I will illustrate via our ongoing mixture model example. So how do we make a Dirichlet process mixture model? We've seen how we make two-component mixture model. We've seen how we make a k-component mixture model. It's time to finally make the infinite component mixture model. So first what we're going to do is we're going to draw the proportions, the probability of every mixture component from our GEM. Done. Now we're going to draw a mean for every one of the components. That's an infinity of means. You wouldn't actually draw an infinity of numbers in practice, and we'll talk about how to do this in a moment, but pretend that I did for the moment. And now what I'm going to do is I'm going to say for each of those means, I'm going to put this probability at the mean. So I'm going to put row 1 at mean 1, row 2 at mean 2. And I'm going to get out this G, this distribution over the means. And these are just two different ways of writing the same thing. So these two lines mean the same as this line. You can think of this line as being a shorthand for these two lines. And what it's essentially saying is, it's another way of expressing that I belong to the cluster with mean mu1 with probability row 1. I belong to the cluster with mean mu2 with probability row 2, et cetera, et cetera. Okay, so now I want to draw which cluster each data point belongs to, and one way I could do that is I could say that Zn, the belonging of the nth data point, is drawn from this categorical. It's drawn from this distribution, just like we were doing before. And now what I could do is I could say, hey, I'm going to give it its own special parameter. This data point, and this data point alone, has a parameter which is mu star n, and that's just the mean of the cluster it's assigned to. So mu sub Zn is the mean of the cluster this data point is assigned to, and I'm just going to call that mu star n. Now, again, there's an equivalent way I could have written things. Oh, so let me just say, here are all of the mu sub k's, well, not all of them, 3 of them. And if I plotted all the mu star n's, well, it would still look the same because they would just overlap each other. And now, here again, I'm writing the exact same thing as these two lines, but compressed into one line. So instead of drawing Zn categorical row, and then giving the nth data point its own special parameter, I could say the parameter for the nth data point is drawn from this distribution. The nth data point has its own special parameter, mu2, with probability row 2, and a lot of these are going to repeat across the n's. And then finally, I draw each data point, the actual observed data point, independently around its mean and with some covariance. Pi. You can change the covariances too. For the purposes of easy illustration, I will not be changing the covariances here. Okay, let's look at this in action. Actually, before we look at the full generative model, let me just come back to this question from before, which was, how does the GEM change as alpha changes? So just to get a sense of what's going on with the GEM, so I know a couple of people came up and talked to me during the break, but I want to make sure we're all on the same page here, because we're about to use the GEM in this full generative model. So let's say that we choose GEM equals 10. Then we get some sort of large clusters, proportionally large clusters in the beginning. And you'll notice things eventually get quite small because we have to have an infinite number of things, an incredibly infinite number of things that add up to 1. So it's just going to have to happen eventually. So this is just plotting row 1, row 2, row 3, ostensibly all the way up to, infinity. But I actually stopped plotting after a while. Okay, and so the question that I want to ask you is, let's say I do the same thing, but I choose alpha equals 1. What's going to happen? What's going to be different? What's going to be the same? Can I get a hand? And can you tell me why? Can you tell me why?
Because alpha is the parameter v1 of the beta distribution we use, and we saw in the beginning that the smaller it is, the smaller the row 1, row 2, row 3, etc.
Great. Okay, so let's think about this together. So the first thing that we do in the GEM is we draw a beta random variable, a beta 1 alpha. And so we drew a beta 110 just now. And so how is the beta 110 going to compare to the beta 11?
In beta 110, we have smaller probability of row that we sample. Like we would have more mass left or to other rows. And in beta 11, we will have roughly the same probabilities.
Great. So the point that was being made here is beta 110. The row 1 of that will tend, on average, this is all random, to be smaller than the row 2. So there'll be a lot of mass left over for everything after the first row. The beta 11, will be on average about the same mass. And so when we plot the GEM1, we see something like this. So again, this actually goes to infinity. There are an infinite number of sticks in here. But they tend to be bigger in the beginning. Okay, let's do one more of these. What happens if I go to 100? So I'm putting a GEM with alpha equals 100. The bars will be more equally spaced. They'll be smaller. Is the answer that I heard. Okay, so certainly they're more equally spaced over here. They're smaller over here. But I will say that it's always a little tough to say something like more equally spaced, because eventually they just have to get very, very much smaller. And so you can talk about something, on this finite level over here, but then eventually you're just going to get these very, very small rows over here. Okay, so now let's go on to looking at the full mixture model.
Question.
Yeah.
Can we have alpha less than 1?
Okay, great question. Can we have alpha less than 1? And I want to add to that, can we have alpha 0 or less than 1? Does anybody have an answer to that?
0.
Why is 0 not possible?
This is the beta distribution, we divide by something.
Great, so here's the answer. Everything that we're doing, we're putting into a beta distribution. And so it has to be an alpha that is acceptable as a beta distribution parameter that will give us a proper beta distribution. And so alpha equals 0 or less than 1 will not give us a proper beta distribution. Okay, so let me talk about what I'm going to be plotting here. So this is our familiar 0 to 1 interval at the top. Ignore everything down here for the moment. And what I want to do is I want to plot this mixture model that I showed you before, this generative mixture model. And so when I was just plotting the GEM just now, I'll tell you behind the scenes what I did, was I just stopped plotting eventually. Like I kept breaking off sticks and then I stopped breaking off sticks. Why won't that work in general?
Because you could sample from something at the very end, ending the center of the category.
Exactly. The problem is I could sample from something beyond what I stopped plotting. Okay, so let me tell you about how I can actually sample exactly from this generative model in general. So what I would like to do in the perfect world is I would like to sample exactly from the GEM. I would have my infinite vector, row 1, row 2, row 3, etc., and it would be infinitely long and everything would be great. And then we know, because we've seen before, that the way that I would sample the indicator variables for each data point is I would put down my uniform random variable for each data point, IID, on the interval, and I would say, okay, my uniform random variable falls into this interval, therefore it belongs to that cluster. Okay, so here's a way that I could go about doing things. Imagine that I actually magically have the ability to sample a countable infinity of things in finite time. It's just magic. So I have magically actually sampled row 1 all the way up to infinity. I've sampled an infinity of these random variables. I just didn't tell you about it. And then I sampled my uniform random variable. Well, in order to tell you what cluster that uniform random variable belongs to, I now only have to show you the beta sticks up to and past that cluster. And I can keep the rest of my secret knowledge of the infinity of random variables to myself. But now here's a way that you could do it without having to have my secret ability to generate an infinity of random variables. You could draw the uniform random variable and draw the beta stick breaks until you're just past it. And that's totally okay because the uniform random variable was always independent of the GEM. I'm going to illustrate this, and then we'll see if there are any questions. Wow, okay, this just happened to be a uniform random variable that was very, very close to 1. In fact, it was so close to 1 that I'm going to run this again, because it does not help my illustration that much. Okay, let's try this again. Okay, well, whatever. I'll deal with it. Okay, randomness, it doesn't always help you. Okay, so I drew my uniform random variable. And what I did was I said, okay, I'm going to break sticks off. So I broke off 1 stick, 2 sticks, 3 sticks, 4 sticks, 5 sticks, until I'm past the uniform random variable, just past it. And I know this will always be a finite number of sticks because the uniform random variable is strictly between 0 and 1. Okay, does everybody get how it is that I can actually make a sample from the GEM, even though the GEM is infinite? I can actually do it in finite time. Are there any questions about that?
Do you ever end up using a count of the number of things by precision?
I'm sorry, what was the question?
Do you ever end up using a count of the number of categories used by precision?
Oh, do you ever have an issue with precision here?
Well, yeah, I think it just seems like if they're exponentially using size or something like that.
Yeah. I mean, you can absolutely run into this sort of thing. So I'm not going to get into the details of making sure that precision isn't an issue. I'll just note that you can do this, and you might have to be careful when you start getting to the really low probability clusters. That's absolutely true. Yeah.
Probably a good question, but what happens if you sample 1? If your sample is 1, exactly.
Oh, so the great thing is the uniform distribution places exactly 0 probability mass on the number 1. And so that will not happen with probability 1. Yes, follow question.
Places 0 probability mass on every number, exactly. So
That's true.
eventually you do hit them.
But it places probability mass 1 on the whole area of numbers between 0 and 1. Getting into some deep philosophical questions here. I'll let you all meditate on this, but I think that we won't run into this problem. Any other questions? Okay, so let me tell you what else is going on in this picture now. So before I was telling you to ignore what was going on down here, and now we will stop ignoring it. Okay, so what's going on down here is I have chosen for my data to exist in the plane, in R2, in two-dimensional Euclidean space. So here I have one dimension of that space, and here I have the other dimension. And I have chosen some particular prior, some normal prior on my cluster means. Or in fact, on my component means. And so what happened is, I said, hey, every component that I figure out what its probability is, I'm going to plot its mean. And so the number of components that I had to figure out the probability for here was 5, right? So 1, 2, 3, 4, 5. And so I plotted 5 black squares for the means. Here, I drew them from the prior. But there's only one cluster at this point. There's only one component that actually has a data point in it. It's this one. And so for that cluster, I said, hey, I know that this data point belongs to this mean because I drew it. Now I have to draw the actual data point value around that mean. There it is. So again, I used the likelihood that I specified. It's a little bit hard to tell because the scaling is kind of off on the screen, but I just chose a diagonal covariance matrix for both the prior and the likelihood. Again, those are things that you could learn in general. This is a lot simpler for me to plot, so I'm just doing it. Okay, any questions up till here? Yeah.
So one thing that bothers me is that this generative process assumes that all the clusters will have smaller and smaller probability. And I mean, do we address this issue like that? Because in the real life, it seems like there's one topic, so it's becoming bigger and bigger, for example, it's bigger.
Okay, great. So the question was, it seems like the clusters have smaller and smaller probability, but it seems like in real life there's one topic that becomes bigger and bigger. What do we do? I would like you to ask that question again at the end of this demonstration and see if the demonstration has answered that in any way. Because I think at least half of the question should be there. Any other questions so far? Okay, if you think of more questions, tell me. In the meantime, I'm going to keep running this. So I plot, so I draw another point. This point happens to fall here into a cluster I haven't seen before. So now I have 2 clusters. And it's drawn around its mean. I actually can't really tell what its mean is from this picture. I'm going to guess this one. But it's drawn normally distributed around its means. This one belongs to the same cluster as the last one, so we draw another point around its mean. For those of us watching at home, it's starting to be pretty clear which one that mean was. Another one. We have a new cluster. We hadn't seen this cluster before, so now we have 3 clusters. Oop, and we just instantiated a new beta stick break, if you can see this all the way down here at the end, because we drew a uniform random variable that was past our previous stick breaks. So we had to instantiate some new probabilities. Get some more data points. No more new clusters yet, or no more new means, but we have filled in all of the instantiated, all of the components that have probabilities now, all have data points in them, so we do have 6 clusters. Now I'm just going to skip ahead. Let's try 10 data points. Let's try 50 data points. Okay, so now I've done 50 data points, and you see that I've gotten one more cluster and a bunch more means. So I had to instantiate a bunch more of those beta random variables. Let's do 100 data points. Let's do 500 data points. And let's do 1,000 data points. Okay, so now we have, something like 1,500 data points. You can see some very large clusters here. And in particular, this one, the biggest blob, is this one giant cluster that we can see up here. And then we see some smaller clusters that are around as well. Okay, so to come back to this earlier question, so one way to come at that question is to say, oh, but I expect that there are some really popular topics that you just get more and more and more people using them. And I would say that that's like this giant cluster here. This topic, if we imagine in this cartoon for the moment that this was topic modeling, tons of documents are using that topic. It's just very, very popular, and it's always going to be the most popular topic at this point. And then there are a bunch of these smaller, rarer topics that exist as well. So is that answering the question, or was there more to it than that?
No, but I think maybe it's not talking about learning when, let's say, we learn about the particular class that corresponds to, for example, topics on Wikipedia, and then new thing comes up. Things appears, and it's supposed to become bigger than how it was before.
Great. Okay. So one question could be, oh, I'm reading stuff on Wikipedia, and then a new topic appears that I haven't seen before, and I actually think it's the most popular. Why doesn't, will that be allowed in this sort of thing? Well, technically speaking, this wasn't the first cluster or the first component. This was actually the fourth component. And so you can imagine if you're doing some sort of learning, it might be that it took you a while to get to that component, but then it would still exist, and you could still learn that it's the largest component. Another thing to think about here is stationary versus non-stationary distributions. And so if you really think that, you're looking at Wikipedia, and there's just a collection of documents, and you think that your documents are, in general, generated IID given some underlying parameters, then you sort of can't get away from this type of model. And in fact, there's a theorem, Kingdon-Painbox theorem, that tells you that if you have exchangeable clustering, then you essentially have to have something that looks like this, that describes the probabilities of your clusters. Another option is you can imagine you have a time series, that actually what's happening is your data is varying in time. So for instance, I read a lot of books because maybe I'm doing a PhD in chemistry, and then I'm just so excited about doing PhDs that after completing my PhD in chemistry, I become a PhD in sociology. And for the next 5 years, I read books about PhD books in sociology. And then I love doing PhDs, so after that, for the next 5 years, I read all about ecology. And so here, there's fundamentally a time series. Like the topics of these 5 years are just fundamentally different from the topics of these 5 years, which are fundamentally different from the topics of these 5 years. And this will not model that. This is a stationary model. It's saying that even though we might not know these underlying probabilities in an inference, we'll learn them, they are the same across all the data. But it could be incorporated into a time series as what's going on in each area of the time series. And that kind of work actually has been done. Yeah?
Maybe some details, but why are the number of means different than the number of clusters?
Right, okay. So let me actually, I'm going to start again this demo in a second. But the idea of the means here is just how many means I made. Because what I was doing is I was saying, I'm going to draw my uniform random variable and make my beta sticks all the way up to that uniform random variable. And then wherever that uniform random variable is, that's the cluster it belongs to. It instantiates a cluster. But those sticks I made along the way, those don't actually have to have any data in them. And so that's the number of means. So it's essentially the number of sticks that I've generated.
Then why wouldn't we stop at 11 means? So that we have 10 clusters?
Yeah, let's run this again. And okay, great. So in this case, it happens to be that my uniform random variable fell into the first stick. When I generated my stick, it already covered the uniform random variable. So the number of means or the number of sticks is the same as the number of clusters. This demo is not helping me. The second one happens to be the same. Let's see if, wow, okay. Let's try this again. Okay, there we go. Okay, so I just started a new demo. Let's all be clear. I started over. I just did n equals 1. And so what I did was I drew my uniform random variable. I drew it over here. And I had to draw 1, 2, 3, 4, 5 sticks in order to cover it. And so that's what this is. This is just the number of sticks that I had to draw to cover my uniform random variable. And so I generated that many means down here, which is why I'm calling it number of means, but it could be number of sticks. And then number of clusters is the number of components with any data points in them, and that's just one. Great. Silly randomness. Okay, great. Any other questions on this? Again, I could run this for lots of data points. And I see that I get these sort of big clusters and these small clusters, and so on. Yeah?
But are you right? So if you choose different values of alpha, the size of the clusters can be different.
Yes, yes, and this was the previous demo when we were doing just drawing the GEM, and that's what essentially we're drawing up here. This is just the GEM. So we saw in that demo that if I draw a GEM with a smaller alpha, then I get these sort of bigger sticks in the beginning. And if I draw a GEM with a bigger alpha, I get these smaller sticks in the beginning.
So choosing the right alpha is very important.
Yeah, it absolutely could. And so it's something that you might want to do something again, like put a prior over, use an empirical Bayes procedure for, something like that if you were actually doing some sort of inferential procedure. Yeah, absolutely. It governs the rate at which you see new clusters, and in fact, I'll tell you the sort of answer. There's one of these exercises. What do we expect to see in terms of the growth of the number of clusters? It's actually alpha log of the number of data points. And so that's something for you to think about. Think about whether that's actually a reasonable growth to see in practice. Is there a question here?
So I was wondering, like here, let's see, one of these sticks is super big.
Yeah.
The other sticks are small or a little bit bigger, and so I was imagining we have some other data points that will come in the future, and there are lots of data points for them, but there is no space in there to be big.
Right. So here's yeah. So the question is, okay. So we have this giant cluster or this giant component. It's really giant, and we have all these other data points that are actually from a different cluster. What do we do? That seems crazy. But here's the thing. This is the difference between the generative model and inference. And so in inference, if you actually have a ton of data from, say, 2 different clusters, then you will learn that, in fact, underlying that, there are these 2 different rows that are all both quite big. And so here I'm saying, supposing these were your rows, this is how your data will be generated. In inference, you will learn the rows from the data. Yeah, that's great. Okay, great. Okay, so I'll just briefly note that, there's nothing specific about the normal distribution here. You could have much more general models. In particular, instead of having a normal prior here, you might have something like if you were doing topic modeling, you would have maybe like a Dirichlet prior, or it could be anything else. It could be any distribution. And in that case, instead of being in whatever normal space, we would be in some other space, some other parameter space, whatever parameter your prior lives in. We have your parameter here. We have G0 here. We might call this theta n instead of mu n. And our likelihood might be different as well. It might be something like, in fact, again, if we were doing topic modeling, something like a categorical itself. This is just to say that this is quite general. And again, there's been a lot of work in this area, and you essentially see it divided between the sort of pre-Markov chain Monte Carlo world and the post-Markov chain Monte Carlo world, where people had computational resources to actually do something on data. And so here we're seeing a lot of the sort of foundational papers in that area where people were starting to use this in practice. Okay, and I want to briefly talk about some of these things that came up and just reiterate them. So we talked about the GEM versus, there are times when you want a small K mixture model. So you want to think about what are the 2 different things that are going on here. Suppose that you actually expect in your data, you are actually studying some very small set of moths or butterflies or something. and you know that there are only 3 species, and you just want to, cluster the moths that are your enclosed, moth space, then you don't want a GEM. You actually just want something that's going to model that there are actually 3 species. Or maybe, you know that there's somewhere between 3 and 8 species, but your lab assistant didn't tell you, and it's really annoying. And so you actually have to figure out how many there are, but you know it's between 3 and 8. And so you put a prior on the number of mixture components. But that's different than in this case where you actually expect the number to be always growing. Here you expect to stop at 8. You know that there aren't more than 8. But here you expect the number to always be growing. And really that's the same thing with the large K mixture model. That, again, here you're going to get growth for a little while like we saw, but eventually you're going to bottom out, you're going to hit K, and here you're not. And again, there was this time series question that came up that, another way that you could always be getting more and more, topics or more and more parameters in your model is you could just have a fundamentally different model over time. Again, something like I could be doing a PhD in one subject, and then 5 years later I'm doing a PhD in another subject, and so on. And there, I just don't think that there's a stationary model that unites these all. I think these are all fundamentally different distributions over the number of topics. And so while you can incorporate a GEM into your time series, you need to have that time series component as well. Okay, so what I'd like to do at this point is start working our way over to inference. And so we've kind of gotten at this issue of the infinity of things being a little bit of a struggle. I have this infinite number of parameters that's sitting around, and well, I can't store those in memory. I can't, update those in finite time. We found a way to get around that with generative models, this sort of trick of, I'll do my uniform distribution for my draw, and then I'll just draw my, components up to that. But then that's kind of problematic when I actually get into inference because, well, I don't know the ordering on the clusters in advance. And so I can't do something as cute as that, at least as easily as that. It turns out there's actually something similar to that you can do, and it's called slice sampling. But we're not going to get into that. We're going to get into another method of inference. And along the way, we'll define what's known as the Chinese restaurant process. Which again, if you know 2 things about Bayesian nonparametrics, if you're going to read papers in the Bayesian nonparametrics literature, there are 2 processes that you have to know, and they are the Dirichlet process and the Chinese restaurant process. Everything else from that will be pretty straightforward. They're usually built in some way on those processes. By the way, an excellent comment came up during the break, which is actually there are 2 branches of Bayesian nonparametrics, one of which you've seen in at least one lecture so far. The sort of continuous branch, the distribution over continuous functions, Gaussian processes. You can get this growing complexity over there too, and it's also Bayesian nonparametrics. Here we're thinking about the sort of discrete side of Bayesian nonparametrics, the Dirichlet process, the Chinese restaurant process, and I'll tell you more things in that ilk later on. Okay, so the idea behind where we're going next is to say, okay, well, if I thought about the beta distribution, if I thought about the GEM distribution before, I had this infinity of probabilities that sum to 1. But when I actually made the cluster assignments, when I drew my z's, those were finite. Those were always a finite variable. And so if I just ignored the GEM values, and I just looked at the z's for any finite set of data, those would be finite. And so if there were some way that I could just sort of deal with the z's and never have to deal with the rows, I'd be set. And so that's where we're going next. We're going to do something where we try to marginalize out the rows. We try to get rid of these underlying probabilities. And again, we're going to do the same sort of thing that we did before. We're going to start by looking at the beta distribution. We're going to go to the Dirichlet distribution, and finally we're going to end up with the GEM or the Dirichlet process. Okay, so the idea here is that we have this generative model for the beta distribution. The rows are beta distributed. Each data point is categorically distributed. The assignment of the data point to a cluster is categorically distributed. 1 with probability row 1, 2 with probability row 2. And what we want to do is we want to find a distribution for the z's that doesn't involve the rows. So the rows never come up. And so we're going to integrate out the rows. This is what we want. We want something where I can say, well, the probability of z1 equals 1 is, there's nothing here at that point because this would be an empty set. But then the probability of z2 given z1 is something, the probability of z3 given z1 and z2 is something, and so on. And I can build everything up without ever touching the rows. And so here, we're just going to work through a derivation together of what this distribution is. Okay, so first I'm just going to use the law of total probability. I'm going to say that this distribution is the same as this one if I put row 1 in and I integrate over row 1. And now I'm going to break this into two parts. I'm going to break the joint into the marginal and the conditional. So conditional on row 1, zn equals 1 is independent of the other z's. And then we have probability of row 1 given the other z's. And can anybody tell me what this quantity is?
Just
Yeah, so what exactly is the number that I should put here?
just row 1.
It's row 1, yes. You're all correct. Okay. Can anybody tell me what this quantity is? Even just a first step, like what does this even mean?
It's a beta distribution updated with the statistics of the classes that we observed.
Yes, exactly. So let's make a first point here. 1, this is the posterior of row 1, given the observation z1 to zn minus 1. We know it's beta distributed because we saw that the beta was conjugate to the categorical. Does anybody happen to know exactly what those beta distribution parameters are?
It's beta with the parameters A1 plus the number of category 1 observations and A2 plus the number of category 2 observations.
Exactly right. So the observation was, and this is, you could say that's an extension of what we derived in an earlier slide. It was also one of the exercises, which admittedly you had very little time to go through, but it's worth going through in your own time later. This is beta, row 1 with 2 parameters, and those parameters are, the first parameter is A1 plus the number of observations that were in category 1. And the second parameter is A2 plus the number of observations that were in category 2. That's what this notation means. Okay, so here all I'm doing is I'm writing out the form of the beta distribution. That's all I've done from this line to this line. And now what I'm going to do is I'm going to take out this normalizing constant and put it over here. I just took that out and I put it over here. And then I notice that everything else that's left, this row 1 to a power, 1 minus row 1 to a power, that's the kernel of a beta distribution. That's the unnormalized beta distribution. And so I know that its integral is the inverse of its normalizing constant. Finally, I'm going to ask you to recall our fun fact about gamma functions, which is that they behave like factorials, and that will let us simplify this. So these A2s, they're going to cancel. This A1 plus 1, A1n, that's going to become A1n. And this divided by that is going to become this. If you didn't follow any of that, that's fine. Here's the punchline. Here are 2 equivalent ways of generating the z's that give the exact same distribution on the z's. And this is the important part. This is the part that you have to pay attention to. You can go back through that derivation later and make sure you understand it. But the important part is I could generate the z's by first generating row and then drawing the z's as 1 with probably row 1, 2 with probably row 2, and just keep doing that. Or I could generate the z's by saying z1 equals 1 with probability a1 over a1 plus a2, and then recurse using this formula. Okay, so let me go into this in a little bit more detail. So the first way that I could do this, the first way, is I first draw the rows. So here are my rows. I drew row 1 and row 2. And now I'm going to draw the z's, and the way that I'm going to draw them is that I'm going to put them into this urn. Why have I drawn an urn? The reason that I've drawn an urn is probabilists love urns. It's something about probabilists. I don't know. I think that they think it's very fancy or something. But this is like an urn that I drew to the best of my skills with Keynote. And so I'm going to put my Z draws into this urn. It'll become a little bit more apparent why I drew an urn later. It won't ever be fully justified. Okay, so I've got this urn, and I'm going to make my Z draws. So I first draw my Z1, and it's going to be orange. It's going to be 1 with probability row 1, 2 with probability row 2. So I draw it, and maybe it happens to be orange. So I've made my Z draws. And then I make another independent Z draw conditional on the rows, and it happens to be green. And I make another Z draw, and it happens to be orange. And I make another Z draw, and it happens to be green. And I do this on and on and on forever. Do this an infinity number of times. And I want you to tell me the limit of the proportion of orange balls over the total number of balls in this urn. It's row 1. Yes, you all got it. And I'm just going to call that row orange. Just because it's orange here. But it's row 1. And even if I had never told you these row 1s, you could repeat this again and again, and I could show you the Z's, and you could discover the row 1s, and you would be left with, if you sort of repeated this experiment again and again, and you plotted a histogram of the values, you would be left with something that's beta distributed because rho is beta distributed. Okay, here I'm going to do something incredibly slightly different, but basically the same. I'm going to start by putting in 3 orange balls and 1 green ball. Why not? I just put in some finite number of balls before I started doing this, and then I did exactly what I just described. I drew my rows, and I started adding extra balls to the urn, these Z balls that were orange or 1 with probability row 1, and green or 2 with probability row 2. And again, I just added a finite number of balls in the beginning, and I stopped. I never did anything again except for what we did before. What's this limiting probability? It's the same. It's row again. Does everybody see that? The finite number of balls can't affect anything. Okay, so now we came up with this equivalent way of filling up the urn. In this case, it is called a Polya urn. This is why I made it an urn. This is an official name that is officially used. Okay, so when I do this, it's called a Polya urn. And what I'm going to do is I'm going to do the same thing, except what I'm first going to do is I'm going to put in, before I begin at all, A1 orange balls and A2 green balls. And now I'm going to say that I draw Z1 with probability, I draw Z1 equal to 1 with probability, number orange balls over number orange plus green balls. Another way that I could say this is I choose any ball that's in the urn with equal probability. I take that ball, I put it back in the urn, and I put in another ball with the same color. It's exactly the same as this construction. Okay, so on the first draw, I draw orange with probability 3/4 and green with probability 1/4. Maybe I happen to draw orange. On the next draw, I draw orange with probability 4/5. Happen to draw green. I do this again and again. Now, we derived on the previous slide that the Z's in this, these balls that I started drawing after the initial balls, have the same distribution as if I drew the row and then the Z. So what is the limiting proportion of the number of orange balls? It's the same. It's row orange, or row 1. And so in particular, here I'm just drawing these Z balls. I started off with a fixed number of orange balls. It was 3, and it was A1. I started off with a fixed number of green balls. It was 1. It was A2. What is the limiting distribution of the percentage of orange balls? Is it fixed? Does it have a distribution?
It's exactly the limit of A1n by the sum of A1
Great, so can you tell me the distribution? Well, so we're saying that, so I start off with this number of balls, this 3, and then I have 1. The next ball is random, right? Its color is random. And then I keep drawing, and at any point in time, I have a random number of green balls and a random number of orange balls, right? And so, but we do think we know the limit of the number of orange balls, right? Row orange. Is that a fixed number? Or is it random? And if it's random, what distribution does it have?
Is beta A1 infinity and beta A1?
Is there a...
Is it beta 3, 1?
Yes, okay, great. Here is the answer right here. It is beta 3, 1. Because I started off with A1 equals 3 and A2 equals 1 balls. Okay, let's go through this again. The point was, these are 2 exactly equivalent ways to generate the z's. One way that I could have generated the z's was the thing that I showed you previously. So before we even got to this, we were here. I said, hey, let me put in 3 orange balls and 1 green ball. That's just some finite number of balls. We can forget about them. And then I generate my z's, IID conditional on the row 1 and row 2. The limiting proportion of that is going to be rho, but rho itself was random to begin with. It was beta distributed. And so if I only showed you the z's, and you ran this to infinity and you plotted a histogram of the proportion of orange balls, and you did that again and again so that you could plot this histogram, you'd see a beta distribution. It would be beta A1, A2. Is that clear? So let's not even go to this part yet. Is that clear from here? And so the key point here is that nothing has changed. We derived that this was exactly the same way to generate colored balls. And so it must be that if nothing changed, that if we draw the balls in the same way, the limit is still going to be row 1, or row orange, and that row was beta distributed. Let me pause here for a moment to see if there are any questions. Okay, so we agree that if I fill up my Polya urn in this way, I start with some initial balls, A1 orange balls and A2 green balls, and I run my Polya urn. I choose any one of the balls with equal probability. Like maybe I choose, I dip my hand in and I find the orange ball. And I put that ball back and I put in another orange ball. I put in another ball of the same color. Then as a result, the limiting proportion will be beta distributed with parameters equal to the number of balls of each color. Now what I'm going to do for handy reference in the future, first of all, let me make a point. So when we talked about the beta distribution earlier, we said that A1 and A2 had to be any positive number. Any positive real number. Well, here it looks like I'm forcing them to be integers. So in order to make this work for any positive number, we'll say, hey, we can have proportions of balls. And we'll just choose the balls with probability proportional to its mass. So they all have the same density. And whenever I pick up a fractional ball, I put in a full ball of the same color. So if I chose this one, I would put it back, I would put back that fraction, but I would also put in one ball of the color orange. Okay, and whenever I run this Polya urn, this process where I run these steps, starting with A orange total mass, say, and A green total mass, I'm going to call this a Polya urn with parameters A orange and A green. Yes?
It's understand why it's important the full orange back and not the fraction.
So the reason that we're putting a full orange back and not a fraction is precisely because of this derivation that we did. So we said that the probability that the new data point is 1 or 2 is proportional to basically the mass of the orange in there. And so it's like we're saying this is a full data point, so we're putting a full data point in. The only reason we would have a fraction is because when we started, we might have a fraction in A1 or a fraction in A2. Great. Okay, let's do it all again, but with more than 2. Exactly the same thing. So now I say, hey, something I could have done is I could have generated a bunch of Dirichlet frequencies. These were Dirichlet distributed, row 1 through row 4. We're totally familiar with this at this point. And then I draw my categorical random variable, Zn. I draw Zn to be 1 with probably row 1, 2 with probably row 2, etc. Turns out you can do the same derivation, and I very much encourage you to do it. It's good for your health. But it's also good to know where this is coming from, but this is exactly what we did. We had that long slide with all of the equations with the beta distribution and the Bernoulli distribution or the categorical distribution. And so you can do the exact same thing here, and you're going to get something that basically looks exactly the same. You're going to say that the probability that Zn equals k is roughly the proportion of data points that have been k so far, where the roughly part is because we start off with some sort of prior mass on k. So it's ak plus number of data points that have been k so far. And this, again, is just a Polya urn. We start off now with a bunch of colors. So here we have some red balls, here we have a tiny bit of a green ball, here we have a yellow ball, and some orange balls. And we do the same thing again. We choose any ball with probability proportional to its mass, and then we replace that ball and add one ball of the same color. So even if it's fractional, we replace the fractional ball, but the new ball we add is an entire ball of the same color. And again, we can say, what is the limiting vector of proportions of numbers of balls of each type?
Exactly row 1k.
Yes, it is the vector of row 1 through row k, which here I've just written as row orange, row green, row red, row yellow, but that's exactly it. And what distribution does it have?
Dirichlet, the original elements.
Dirichlet with the original A's, I'll say, in this case. Yes, so it's Dirichlet with the original A's. Dirichlet A1 to AK. Dirichlet A1 to A4 in this case because we had 4 colors. Are there any questions so far? Yes?
So this Polya urn operator is a way to sample from the Dirichlet. So in like taking samples.
Yes, exactly. What we are doing here is exactly taking samples from the Dirichlet. We have taken samples from the Dirichlet here. All of these are samples from the Dirichlet. So let me be a little bit careful there. Technically speaking, a sample from the Dirichlet is this, but we are taking samples from the probability that was generated from the Dirichlet. And so that's what we're doing here. We're taking samples from that distribution again and again and again. And so this is a way to do that without ever having actually drawn the row.
So it means that if you take 1,000 samples, then you take one sample of the Dirichlet. You take one row distribution.
Yeah. So if you take 1,000 Z's, they're all coming from the same row here. Exactly. You'd have to start the whole thing over, your whole Polya urn over, to get a new Dirichlet. Dirichlet distributed in row. Yeah?
I'm wondering, how do you initialize this? Because at the beginning, if you have only a few rows, then the distribution will change a lot.
Yeah, how do you initialize it? The initialization is actually exactly the parameters of the Dirichlet. That's the number of balls you put in. And it seems kind of crazy. You'd think that like, oh wow, you know, shouldn't it just like all go over to this side or all go over to this side? And the amazing thing is that you actually get this distribution out for the proportions in the end. And it's just the randomness. Sometimes it can happen that everything goes one way, and sometimes it can happen that everything goes the other way.
So it's a rich, so they need to repeat the process a lot of times.
Yeah, so if you repeat the process a lot of times, it's like drawing this row a lot of times. Yeah.
So do we have any idea of the speed of convergence of each of the empirical estimators, like number of arranged times by number of total?
I'm sure we can absolutely say something about that. I mean, what's essentially happening here is some strong law of large numbers kind of thing. I'm not going to get into that question though, because I want to get on to telling you how this is related to the Chinese restaurant process. Okay, surprise, this is related to the Chinese restaurant process. Before we get there, we're gonna go through one more urn. And basically, the thing is here, we want to think about, okay, you know, last time we went beta, Dirichlet, GEM. So 2, K, infinity. And so that's what we want to do here. We want to say 2, Polya Urn, K, multivariate Polya Urn, infinity, what is that? And so there's kind of an awkward thing here because I can't actually fit an infinite number of balls into my urn. It's a finite urn. So what am I going to do? And the answer is, I'm going to introduce a magical special ball that looks like this. So we will make this ball colored black, and we'll say it's like some magical 8 ball. And so special things happen with the magical 8 ball that didn't happen in the previous urns. And by the way, when we have this special magical 8 ball, we have what's known as a Poppy urn or a Blackwell-McQueen urn. Okay, so here's what happens. We're going to do the same thing we did before. We're going to choose any ball with probability proportional to its mass. This is really easy on the first draw because there is literally only one ball. Let's call its mass alpha. It turns out that there will be no coincidence that I called it alpha. But let's call its mass alpha. So it has some mass. We're going to choose a ball proportional to its mass. That's obviously the ball we're going to choose first. If we choose the magical special magic 8 ball, then we will replace that 8 ball, but we will add a ball of a new color, a color we've never seen before. On the other hand, if we pick up a normal ball, a ball that is not a magical special 8 ball, then we will replace that ball and add a ball of the same color. Okay, so let's run through this. What does this look like? Well, on step 1, we don't have any choice. We have to choose the magical special 8 ball. So we get a ball of a new color that we haven't seen before. On step 2, we could choose either this ball with probability proportional to alpha or this ball with probability proportional to 1, because it's a full ball and has mass 1. And so it just so happens that maybe we chose orange. Step 3, maybe we chose the black ball, and so we choose a new color, a color that didn't exist in this urn before. Step 4, maybe we chose the black ball again, so we choose a new color, a color that maybe didn't exist in this urn before. Okay, so I have a question for you, and that is, suppose that I start on step 1, and I look at, starting from step 1 forward, the number of balls that are orange and the number of balls that are not orange. So I have this tuple of counts, number of balls that are orange, number of balls that are not orange. Can you tell me the distribution of that sequence? Here are some distributions that you know. Beta, Dirichlet, GEM, Polya Urn.
Beta 1 alpha.
So I'm looking for a distribution of a sequence of counts. Would the beta give me that? The GEM would also give me real value numbers. So I'm looking for a distribution of counts, a tuple of counts of orange and not orange balls. I hear Polya Urn. Awesome. What are the parameters of that Polya Urn? Remember, the Polya Urn has 2 parameters. Do you remember what those Polya Urn parameters were, what they meant?
Initial.
It's going to be alpha and then 1. Right?
Great, okay, so let's go over this. So one point here was made, which is the Polya Urn parameters are the initial number of balls of each type. And then the comment made over here was, we start with 1 orange ball and alpha not orange balls. And so the distribution of the sequence of orange balls and not orange balls going forward is a Polya Urn 1 alpha. Because if I choose an orange ball going forward, I always replace it with an orange ball. Or I replace it and I add 1 orange ball. If I choose not an orange ball, I always replace it and add not an orange ball. Even if I choose the black ball, I still replace it with a not orange ball. Or I still add a not orange ball. Okay, let's see if there are any questions on this. Yes? Yes, the mass of the black ball is always alpha. And so at step 1, there's alpha not orange mass, and there's 1 orange mass. And that's why we have Polya 1 alpha.
Sorry.
Yeah.
You say that we cannot take alpha equal to 0, but can you explain what's going on if alpha tends to 0? The intuition is that the Urn will always be empty, because at the first step we cannot choose something of mass 0.
Yeah, well, so let's think about what happens with alpha very small. So with alpha very small, well, you have no choice on step 0. There is only one thing that you can choose. So you will always immediately get another ball. But then you'll be very unlikely to choose the black ball in the next step, because this has mass 1 and this will have mass very tiny. Yeah. Okay, new question for you. Suppose I ignore the orange balls. Pretend they never existed. What is the distribution, starting on step 3, of the pair of, or the tuple of number of green balls, number of not green balls? Love to see some hands or some shouts. Can you tell me exactly? Yes, it is the Polya Urn with 1 alpha. Because again, starting here, I can ignore the orange, they just perpetuate themselves. But if I draw green, I get another green. And if I draw anything that's not green, I get something that's not green and not orange. So it's Polya Urn 1 alpha going forward. Okay, and I'll just tell you the answer to if I ignore green and orange here, and I look at number of red, number of not red, surprise, it's Polya Urn 1 alpha. Okay, why is this important? Well, we know the limiting distribution of the proportion of orange in a Polya Urn 1 alpha. Does anybody remember the distribution for that? Beta 1 alpha. Exactly. So the limiting distribution of the proportion of orange in this crazy, hoppy black hole McQueen urn is beta 1 alpha. Now supposing I get rid of the orange, then the limiting distribution of the not orange things that are green is also beta 1 alpha, because that's the limiting Polya Urn distribution. And supposing I get rid of the things that are orange and green, the limiting distribution of the things that are red is beta 1 alpha. Does this sequence look familiar?
Stick breaking.
Yes, it is stick breaking. It is GEM stick breaking. If we run the Polya Urn, it is equivalent to having done GEM stick breaking and then making categorical draws from those probabilities. And that's what we've seen here. And this is fundamentally a finite thing. We never had to draw the GEM probabilities. We didn't have to draw, this infinity of probabilities. All we had to do was run this crazy urn. And there's always a finite number of balls in this urn. This is something we can definitely keep track of. Okay, I'm going to show you the exact same generative model. The exact same generative model as this urn, but I will call it something different I will call it a Chinese restaurant process. Okay, the Chinese restaurant process works in the following way, which is what we just did. A customer walks into the restaurant. This is the ball that's about to be assigned a color. They sit at an existing table with probability proportional to the number of people who are there, and they form a new table with probability proportional to alpha. The new table is the black ball. Every existing table is a color of ball. So the first person walks into the restaurant. There is no existing table. There's only the possibility of a new table. There's only the black ball to be chosen. And so they form a new table. And typically with the Chinese restaurant process, we imagine that a dish is served at the table. That dish, we'll call it phi 1. That is like the cluster-specific parameter, like the mean in a mixture model. Delicious, delicious mean in a mixture model. Okay, the next person comes in. They have the option to sit at an existing table with probability proportional to the number of people who are there. There's one person here, or they can sit at a new table. They can choose this color of ball, of which there is exactly one in the urn, or they can choose the black ball. So the second person comes in, and maybe they just sit here. The third person maybe chooses the black ball, and so they form a new table, and they put a dish at that table. That's maybe the cluster mean against some cluster-specific parameter. The fourth person comes in, they sit at this table in proportion to the number of people who are here. There's 2. They sit at this table with probability in proportion to the number of people who are here. That's 1. They sit at this table with probability in proportion to alpha. This is the black ball. This is one color of ball, like there's one yellow ball. This is one color of ball, like there's 2 orange balls. And we just keep running this. Okay, are there any questions so far? Yeah.
So is this the reason why we want to keep the outputs like the same? If the means were drawn from different mean distributions, then we wouldn't have these equivalents?
Yeah, so it turns out, so the question was, is this why we wanted to keep the A's and B's to be 1 and alpha in our earlier construction? If they were the same, would we not have something nice like this? It turns out, actually, that in another very special case, which is related to something called the Pittman-Ure process, you actually do have a construction like this, but it is a very special construction, and it's not general, and it's not something you would generally have. Yeah.
So I'm confused. Is Chinese restaurant process exactly the same as GEM concept?
Yeah, so the question is, how does the Chinese restaurant process relate to the GEM process? And so the difference is, so here are 2 things that you could do. You could draw your GEM, row 1, row 2, row 3, row 4, etc. And then you could draw categorical random variables from them. You could say Z1 equals 1 with probably row 1, etc. Z2 equals 1 with probably row 1, etc. and so on. And now you've got your Z's. And you could say, hey, all of the Z's with the same number, like all of the ZNs that are equal to 1, sit at a table. And all of the Z's that are equal to 2 sit at a table. And all the Z's that are 3 sit at a table. And those Z's would have the exact same distribution as if you had run this Chinese restaurant process.
Okay, so this is like a special case of GEM, because in GEM you have like something like distribution.
It's not exactly a special case of the GEM. Rather, I would say it's the marginal of the GEM with the categorical draws on top. It's the distribution of those categorical draws if you marginalize out the GEM.
Okay, because this also is like do something from Gaussian.
Oh, so there's no Gaussian that comes up in the GEM. So that's later part of the mixture model, and you can add this to the mixture model later as well, and we'll see that. Yeah, great. Yeah. On the previous slide. Oh yeah, exactly. So yeah, let's just go back there. So the rows, so the V's, the proportions are the beta 1 alpha, and then the rows are sort of, the multiplying 1 minus all of these up to the last fraction that you break off. So they're these stick breaking break off probabilities. Yeah. But they're exactly the same as the GEM. Okay, so far what we've done is we've seen the Dirichlet process, we've seen the Chinese restaurant process. I hope, especially with that last conversation, that you have a sense of how they are different and how they are the same. In particular, that if I have the GEM with the categorical, that categorical set of draws is the marginal, its marginal is the same as the Chinese restaurant process. And again, we're getting the sense of there's this infinity of latent parameters, but effectively in the data, there's a growing number of parameters, a growing number of actual parameters that we see in the clusters that are actually instantiated. And that's what we're seeing here with the Chinese restaurant process, that as we draw the black ball more and more, as we make new tables, we're getting a growing number of tables, a growing number of clusters. Even though effectively hidden somewhere there's this GEM infinity, here we've been able to marginalize it out. And so what I'd like to do now is take a brief break after, again, I introduce you to some quick exercises, and then we will come back and finish off this story with some inference. And hopefully some talk of other things that exist in Bayesian nonparametrics, sort of a brief tour into the other ideas that are out there. Okay, so some exercises, something that would be useful before the next set of slides is to just briefly refresh yourself on Gibbs sampling. Maybe look at the Wikipedia page or just remind yourself what that is. But I am going to use it very briefly, and so it might be useful for you to have that in mind. And you might think about what are the advantages and disadvantages of using a Dirichlet process versus using a Chinese restaurant process. Perhaps for inference, for generating things, anything like that. They're both used in practice. I actually just told you this earlier, but you can actually derive it now from the things that we've done in these previous slides. You can actually derive the exact formula for the expected number of clusters generated by a CRP alpha after n data points. This might be something for sort of later when you have time, not necessarily during this short break. And so I said that, so you're gonna get an equation here that will asymptotically look like alpha log n. And you might ask yourself, what do you think about that when it comes to real data modeling? Is that reasonable? Is that a reasonable rate of growth? And then something, again, this is probably definitely for later on when you have time, but code your own CRP, at least generative model. Examine the empirical distribution. You can see how the number of clusters grows with the number of data points, but you can also look at the number of clusters after n data points over multiple runs. And that'll be an empirical distribution over the number of clusters for a fixed n data points, and you can see what that distribution looks like and whether that distribution is reasonable. Okay, so let's break right now for about 15 minutes and come back about 12:20, if that sounds good.